Am I clearly audible? And is my screen visible in the full screen mode? Yeah.
Yes, sir.
All right. So let us start the session. So we'll continue with the same topic that we were discussing in the last session, that is ensemble learning. Right. So in the previous session, we have discussed the two ensemble learning techniques, two or three ensemble learning techniques, bagging, ADA boosting, and mixture of experts we had discussed. Okay. So the advantage of this ensemble learning technique is that they combine the multiple weak learners to form a strong nonlinear hypothesis. So gradient boosting is one such technique, right? But it is very interesting idea, right? So we have seen boosting technique already, but that is ADA boosting technique. So in the ADA boosting technique, what we are doing at every iteration, we're learning a weak learner. The algorithm is learning a weak learner to compensate the shortcomings of the existing weak learners, right? So, and the shortcomings of the existing weak learners are identified through weighted data points, isn't it? So through the weightage of the data points, we are identifying the shortcomings of the existing learners and learning another weak learner to compensate the shortcomings of the existing weak learners, existing models or hypothesis, right? So the idea is similar here also, but the way we identify the shortcomings of the existing weak learners is different. Okay, so that's the only difference between the ADA boosting and the gradient boosting. So if you recall this ADA boosting technique, so initially we are assigning equal weightage, we are giving equal weightage to all the data points. Learning a hypothesis weighted as per this learning a hypothesis that minimizes the weighted loss weighted as per the data set at that iteration. Now we are upweighting all the misclassified instances and downweighting all the correctly classified instances. Learning a hypothesis that minimizes the weighted loss. And again, upweighting, downweighting, learn another hypothesis. So this process is repeated multiple times. So if you see the process, what are we doing here? We are fitting an additive model in the forward stage-wise manner. So at each stage, we are introducing a weak learner to compensate the shortcomings of the existing weak learners, right? And here, in the ADA boosting technique, shortcomings are identified by high weight data points, right? So now we're going to discuss the gradient boosting algorithm, which is the combination of the gradient descent algorithm plus the boosting. So the concepts, both the concepts are borrowed to model this gradient boosting algorithm. All right. So in this, the process is same, but the way we identify the shortcomings is different. So here also, we'll fit an additive model in the forward stage-wise manner. In each stage, we introduce a weak learner to compensate the shortcomings of the existing weak learners. But in case of gradient boosting, shortcomings are identified by gradients, right? Whereas in case of ADA boosting, we were identifying the shortcomings using the high weight data points. That is the only difference between the ADA boosting and the gradient boosting. In the gradient boosting, shortcomings are identified by gradients. Okay, so whatever it is, both the high weight data points or the gradients tell us how to improve our model. All right. So the process is this. Simple idea is this. How it does that, we will see later. The complete procedure. But this is what it is doing. This is what we are doing in case of gradient boosting algorithm. We are fitting an additive model in the forward stage-wise manner. At each stage, we are introducing a weak learner to compensate the shortcomings of the existing weak learners. And how are we identifying the shortcomings? Shortcomings are identified through gradients. All right. So we'll see an example, then you will understand it better. So forget about the problem for a while and let's play a game, right? So let us say that you are given a data x1, y1, x2, y2, so on, x and yn. And the task is to fit f of x to minimize the squared loss. You know this, right? Let's take a house price prediction problem. We have given x1, y1, x2, y2, so on, x and yn. the task is to minimize the squared difference between actual and the predicted values, right? So the task is to learn f of x, which is the predicted value, so that the difference between the squared difference between actual and the predicted values is minimized. So this is what is the task. So suppose your friend wants to help you and he gave you this function f. He gave you this hypothesis f, right? So you check his model, you have checked his model, and you found that your friend model is good but not perfect. So in a sense that there are some mistakes. If the actual value is 0.9, your friend model predicting it as 0.8. If the actual value is 1.3, your friend model predicting it as 1.4. It's a good prediction, but it's not the perfect prediction, right? So there it means there are some deviations between the actual and the predicted values. Now the question is, how can you improve this model? How can you improve this model? So wait a second, because there are some rules for the game. All right. So the rules for a game is that you shouldn't make any changes to the parameters of the f, or you're not allowed to remove anything from f, or you not change anything. You're not allowed to change any parameter in the f, right? So how can you improve your friend model without making any changes to the parameters of the friend model? Any answer? Understood the question? Understood the question, right?
So once again, question please.
See, you are given a data set x1, y1, x2, y2, so on xm, yn. Okay, you want to learn some function f of x, which is the hypothesis, such that the square difference between f of x and y is minimized. For all f of xi and yi is minimized for all I. It means sum over I equal to 1 to m f of xi minus yi whole square. You want to minimize this. So you want to learn some function f of x so that the square difference between actual and the predicted values is minimized. Right? Is it clear so far? Is it clear?
Yes, sir.
Yeah.
Yes, sir.
Your friend want to help you and he
Yes,
gave
sir.
you this model f. Okay. You have checked his model and you found that this model is good but not perfect. So in a sense that suppose if yi is 0.9, y1 is 0.9, your friend model predicting it as 0.8. If y1 is 1. y2 is 1.3, your friend model predicting it as a 1.4. That means there are some small deviations between the actual and the predicted. Right? Clear? So far, is it clear?
Yes.
Right. Now the question is, how can you improve your friend model?
By adding error component.
Adding or subtracting. So just adding and subtracting some component into y1 or y2, then we can attempt this.
Okay, great.
Sir, by adding error component one more to make up
One more
the
component.
Yeah.
Great. So your friend model predicting it as f of x1 equal to 0.8. Okay, but y1 is 0.9. So now what you're suggesting is that you add another component, another function, right? If you, because you're not allowed to make any changes to f, add another hypothesis h of x1, so that f of x1 plus h of x1 is equivalent to y1. Right? This is what you are suggesting, right?
Yes, sir. Yes, sir.
Yes.
Right. Fine. So that's very much good. I mean, so we can add an additional model h to f so that the new prediction will become f of x plus h of x. How do we do this? How do we do this? We wish to improve our model such that f of x1 plus h of x1 equal to y1, f of x2 plus h of x2 equal to y2, and so on. F of xn plus h of xn is equivalent to y1. Right? It means for what I have to fit this h of x? I have to fit h of x to y minus f of x. Am I right? It means I want
Yes.
to learn this h of x1 such that h of x1 is equivalent to y1 minus f of x1. Similarly, y2 is equivalent to h of x2 equivalent to y2 minus f of x2, and so on. H of xn is equivalent to yn minus f of xn, isn't it? So you want to fit a model to this residual parts where the existing model couldn't do well, isn't it? So it means you are trying to fit another model to compensate the shortcomings of the existing model, right? And the shortcomings are these residual parts, right? So we can any regression tree achieve this goal perfectly? Can any hedge can achieve this goal perfectly? Maybe not, but some regression model can approximate it. Okay, so but some regression model might be able to do this approximately. All right, so how we do this? We just fit a regression model to this x1 comma. Instead of fitting a regression model for y1, now we are fitting a regression model for the residual part, y1 minus f of x1. Instead of fitting regression model for y2, we are fitting this regression model for y2 minus f of x. So please see that our target values are changed now. We are not fitting the regression model to the original target values. Okay, we are fitting a regression model to the residual parts where the existing model couldn't do well. Clear? Is it clear so far?
Yes, sir.
Yeah, every word. Is it clear? That's
Yes, sir.
Yes, sir.
all right.
Yes, sir.
So good. Congratulations. We've got a better model, right? So here yi minus f of xi are called the residuals. So these are the parts that the existing model cannot do well. So the role of this new hypothesis H is to compensate the shortcomings of the existing model F. Now there is another question coming in here. What if you're still not satisfactory with F plus H also? You're still not satisfied with F plus H also. What will you do?
Again adding
One
some
more?
Repeating the
this
same
parameter.
procedure.
Yeah. Yeah. So if the new model F plus H is still not satisfactory, we can add another regression model, right? To compensate the shortcomings of both the existing models. Okay. So now another question that is coming in here is that we are improving the predictions of the training data. Is the procedure also useful for the test data? So of course, yes, because we are building a model, F plus, H plus, Z plus, whatever. We are building a model. So the model can be applied for any data, train data or test data, whatever it is the data, right? Yes, because we are building a model and model can be applied to test data as well. All right. So now the question is, how is this relevant to the gradient descent algorithm? So far we understood the algorithm. Algorithm is very simple. We are learning a model, f of x, right, and computing the residuals and fitting another regression model to the residuals. If you are still not satisfactory, again compute the residuals, fit another regression model to the residuals, and so forth. Okay. Now the question is, how is this relevant to the gradient descent algorithm? How is this relevant to the gradient descent algorithm? So all of you remember
gradient, sir, in gradient descent, we try to approach the local, the optimal this thing. No, there also we are trying to approach the.
Yeah, yes, true. Let us elaborate that. Okay, what you said is right. Let us elaborate it. Do you remember the gradient descent algorithm? What is it doing? It is learning the optimal parameters, right? Right? By moving in the opposite direction of the gradient, right? So you see that, do you remember this updation rule? Theta equivalent to theta minus some alpha, or here it is given as a rho, but you can take it as alpha, learning rate, whatever it is. So theta equivalent to theta minus alpha times the derivative of j with respect to theta. So do you remember this updation rule? What is it doing? If this gradient is positive, what is it doing? It is decrementing the corresponding parameter. If the gradient is negative, then it is incrementing the corresponding parameter. Am I right? Do you recall this? Everybody, do you recall this?
So
Yes, sir.
we have to recall.
So it means what? It is moving in the opposite direction of the gradient. If it is positive, then it is decrementing. If it is negative, then it is incrementing. It is it is moving in the opposite direction of the gradient to minimize the loss function, right? So this is what it is doing. So now in our model also we wish to improve our model, right? We wish to improve our model by updating the model, right? It means you're not updating the parameters of the model, but you're trying to add an additional component to the existing model, right? So in our thing, this is the loss function, squared loss function. We want to minimize the squared difference between actual and the predicted values. But this time we don't want to adjust the parameters. We want to adjust the function itself, right? So we wish to improve this model by adjusting f of x1, f of x2, so on, f of xn. So please remember, like you take any algorithm, regression algorithm that you know. What are you doing? You are improving the model by adjusting the parameters of the model like this: theta equivalent to theta minus derivative of j with respect to theta j. So if you wish to improve by adjusting theta values, you are taking the gradient with respect to theta. But here you wish to improve the model by adjusting the f of x1, f of x2, so on, f of x1. And what are these f of x1, f of x2, so on, f of xn? They are just some numbers. They are the prediction values. So therefore, you can treat them as a parameters and take the derivative with respect to them, right? So when you take the derivative of j with respect to f of xi, what is the derivative of j? What is the loss function? yi minus f of xi whole square by 2, isn't it? So when you take the derivative of this loss function, what will you get? You will get y minus f of x. This square will come this side. The square and divided by 2 will get cancelled. Divided by 2 will get cancelled. Yi minus f of xi. And derivative of this again you compute. Derivative of this is, when you take the derivative of this with respect to f of xi, you will get minus 1. Right? So minus 1 multiplied by yi minus f of xi, which is equivalent to f of xi minus yi. Isn't it? Are you getting this or not? When you take the derivative of this loss function with respect to f of xi, what are you getting? You are getting f of xi minus yi. Okay. So what is this f of xi minus yi? Isn't it the negative gradient? So you see this, yi minus f of xi is the residual part that we were trying to compute. I mean, we're trying to fit a model to this residual part yi minus f of xi. So what is this f of xi minus yi? Isn't it the negative, sorry, f of xi minus yi is the derivative of j with respect to f of xi. And here, therefore, we proved that residual is equivalent to the negative gradient. Clear? Have you are you agreed for this? Residual is equivalent to the negative gradient. Do you agree for that?
Yes, sir.
Do you agree with it? Yes.
Yes,
Yes,
sir.
sir.
Residual is equivalent to the negative gradient. It means fitting a regression model to the residual is equivalent to fitting a regression model to the negative gradient. Am I right? Fitting a regression model to the residual is equivalent to fitting a regression model to the negative gradient. Am I right?
Yes, sir.
Right. It means what? Updating a model based on the residual is equivalent to updating a model based on the gradient. That's why it is called gradient boosting algorithm. All right. So f of xi is equivalent to f of xi. You wish to improve our model by like this, by updating the model like this: f of xi equivalent to f of xi plus h of xi. And h of xi you are fitting for the residual yi minus f of xi. And this is equivalent to fitting a model to the negative gradient with alpha equivalent to 1. Right? So it means updating a model based on the residual is equivalent to updating a model based on the gradient. So f of xi is equivalent to f of xi minus 1 times the derivative of j with respect to f of xi. Isn't it looking like a gradient updation rule? Theta equivalent to theta minus alpha times the derivative of j with respect to theta. Isn't it of the same form? Right. So residual is equivalent to the gradient. Acha, please make note of one line here. This is the regression with the squared loss, not for any other loss. This will will come to this point later, but just make a note of it. So this is with the regression with the squared loss. For the regression with the squared loss, residual is equivalent to the negative gradient. So it means fitting a model, regression model H to the residual is equivalent to fitting regression model to the negative gradient. It means updating F based on the residual is equivalent to updating F based on the negative gradient. Alright. So that is why it's called gradient boosting algorithm, which is gradient descent plus boosting concept. What boosting concept is? At every stage, introduce a weak learner to compensate the shortcomings of the existing weak learners. And the shortcomings are identified through residuals. And residuals are equivalent to the negative gradients here. That means updating a model based on the residual is equivalent to updating based on the negative gradient. It means identifying the shortcomings through the residual is equivalent to identifying the shortcoming through negative gradients. That is why it is called gradient boosting algorithm. Okay, so we are actually updating our model using the gradient descent algorithm. So is the concept clear so far? Are you with me?
Yes, sir.
Yes.
Yes, sir.
So it turns out that the concept of the gradient is more general than the concept of the residual. So from now onwards, we'll stick to the concept of the gradient, not to the residuals. Okay, so you will understand this reason soon, right? Why is that we are sticking to the concept of the gradient? The reason is very simple, right? So if you formulate this algorithm using the concept of the gradient, it can be generalized to any loss function, not just the square loss function. See, here we are saying that residual equivalent to the negative gradient only for the squared loss. Okay, this is not true for the other loss functions. But if you can formulate the algorithm with the concept of the gradient, this can be extended to any other loss function. All right, that is the reason why we use this. So this is an algorithm to summarize the steps. Let us summarize it. Regression with the squared loss. Okay, so compute the negative gradient. Negative gradient is equivalent to the residual. All right, so start with an initial model, any weak learner. Here the average value they have taken. So iterate until convergence. Every iteration, calculate the negative gradient, fit a regression tree to the negative gradient, and update the gradient f equal to f plus h. Sorry, update the model f equal to f plus h. Right. So this process is repeated multiple times. All right. So is the algorithm clear? Is the algorithm clear? Very simple algorithm. Start with the initial model, calculate the negative gradient at each step, fit a regression model to the negative gradient, update the model f equal to f plus h. Right? So clear, right?
Yes,
Okay.
sir.
So the benefit of formulating this algorithm using the gradient is that it allows us to consider the other loss functions and derive the corresponding algorithm in the same way. Right? So now another question coming in here, that why is that we have to consider the other loss functions at all? Why should we consider other loss functions at all? Isn't it the squared loss good enough? Right. So what is the reason behind considering the other loss functions? Okay. So why do we need to consider other loss functions? Isn't it the squared loss good enough? So let us try to understand what is the problem with the squared loss function. Okay. So for that we'll be taking one example here. So the problem with the squared loss is that it is not robust to the outlier points. It is easy to deal with mathematically, but it is not robust to the outlier points. What do we mean by it is not robust to the outlier points? Okay, so you see this example here. If yi equivalent to 0.5 and f of xi is 0.6, the squared loss is adding a penalty of 0.005. This is the squared loss, y minus f whole square by 2. If this is 1.2 and this is 1.4, then it is adding a penalty of 0.02. This is 2, this is 1.5, adding a penalty of 0.15. You see this case, here it is a 5. Clearly it is outlier because it is very different from the other data points, right? So this is an outlier point and the prediction is saying it is 1.7. So one of the characteristics of the squared loss is that the more the prediction is deviating, the more penalty it adds. So now it adds a penalty of 5.445. 5.445. So because it's adding of so much penalty, what is the objective? Objective is to minimize the overall loss, right? So it means it will try hard to fit this outlier point into the model. If you haven't got the visualization, let me give you an idea about this. So let's say that all these points are somewhere here. The data set is something like this. There is one outlier point somewhere here, right? So there is an outlier point. So suppose if I fit a line something like this, it adds a too much penalty with respect to this point and it increases the overall loss. So because our objective is to minimize the overall loss, it will try to adjust the line towards this outlier point. So it means as a result, you may get some line like this, right, which is not capturing the trend of the data. As a result, overall performance will be degraded. So if you try hard to incorporate this outlier point into the model, it will be biased towards the outlier point. As a consequence, the overall performance will be degraded. So that is the problem with this squared loss function. Outliers are heavily punched because the error is squared every time, right? So as a consequence, it pays too much attention to the outlier points and it tries hard to incorporate outlier points into the model that will degrade the overall performance. So have you understood what is the problem? Why that we are saying that it is not robust to the outlier points?
Yes, sir.
Right. So this is not
Sir,
robust to the
so sorry to say, but normally, while we do some exploratory analysis and all, at that point of time, we identify the outliers.
yes.
We remove outliers generally we remove outliers at that point of time only. Then why during the model training again we are dealing with the outliers? We know because outliers, if presence of outlier will lead to the performance degradation. That's why we remove them earlier only, no sir. Now again.
If you do it so, yes.
Okay. If you
If
don't
you do it, yeah, if the model has to take care of it automatically, then we are talking about that case.
okay.
Without doing any pre-processing. Or if there are cases that where you can deal with the outlier points also. These two cases, this is useful. Okay, madam.
Oh, okay, sir.
Yeah. So this degrades the overall performance. Fine. So how to handle this? Right. That is why we need some alternative loss functions, like the absolute loss. Right. It is more robust to the outliers, or the Huber loss. Right. This is applying squared loss if the difference is less than certain threshold. Otherwise, some function of absolute loss it is applying when the difference is greater than certain threshold. Now we'll see the same example with respect to this absolute loss and the Huber loss as well. Now you see this is the squared loss. For this outlier point, it is adding a penalty of 5.445. Absolute loss is adding a penalty of 3.3. Huber loss with delta value 0.5, adding a penalty of only 1.525. It means it's not paying too much attention to the outlier points. Okay, it means it's a kind of some way of avoiding this outlier points. All right. So now we can formulate the gradient descent algorithm with respect to the other loss functions as well. So compute the negative gradient, start with an initial model, calculate the negative gradient at each and every step, Fit a
Sir, what is
regression
the
model.
initial model? I could not.
This here it is taken some simple models, sir. Average of all the output values as the initial model, initial prediction.
Initial
Average,
prediction.
sir.
For
Average.
a sample
All
or
the target values average you take. That is, it can be anything, sir. It not necessarily this only, but here I have taken a simple averaging model.
initial value for for parameter f of x.
That's not parameter. Yeah,
Okay.
it's a function, but you are just considering as a parameter to update the values. So initial model is just the average set, average of all the target values here, but it's
Yes.
not necessarily the same always. You can take any model, you can take the linear regression and continue to it. Anything is okay. Okay.
Okay.
Clear, sir?
Okay.
Any query, any further query, you can ask.
Sir, this one gradient descent, once you add the component, it will become a linear. Can we think of theta 1 fx, f of x plus theta naught? Is it like that? That last will be again y of e minus f of x.
No, don't do it. No, it's not like that. Okay, loss can be anything. It's not necessarily that yi minus f of x. It can be anything. So with whatever is the loss, you compute the gradient with respect to the loss.
Okay.
So here you're taking the absolute loss. When you compute the gradient with respect to the absolute loss, you got this as a gradient. It's not the residual.
Okay.
See, observe that. That's not exactly residual. Just the
Sir,
sign of yi.
is it you are following stochastic gradient here? Stochastic? You are,
No, it's not stochastic. It can be anything, sir. Doesn't
no,
matter. That
until
is.
you until you iterate until convergence. Like
Oh, that
for
is the. I mean, see,
every
every
time you
iteration, updating the model, or you're adding an additional model to compensate the shortcomings of the existing model.
okay.
Yeah. So it's not like, I mean, within that, when you are updating it.
Here I got confusion like f is equal to f plus. If it is f1, f2, then would have been better, sir. And f2 would be encapsulating f1 and other
No, it's
components.
like this. See, when I
Yeah.
say f equal to f plus h, what are you doing? You are adding like f of x1 equivalent to f of x1 plus h of x. F of x2 equivalent to f
Okay.
of x2 plus h of x2 and so on.
Okay.
Okay. So it's not that
Okay.
just one I think that you're just doing over all the instances. F
Okay.
equal to, yeah, this is the vectorized notion. Yeah. So if you generalize the process, get any differentiable loss function, start with the initial model, calculate the negative gradient, fit a regression model to the negative gradient. So update the model f equal to f plus h. Right. So in general, negative gradients are not equivalent to the residuals. But we should follow the concept of the negative gradient rather than the residual. Why? Because the negative gradients are more robust to the outliers than the residuals. Okay, let us see with an example. Okay, so this is the negative gradient versus the residual example. Right. So let's take a Huber loss. Right. When you're taking the Huber loss, this is the loss function. When you take the negative gradient with respect to the Huber loss, this is what you get. Yi minus f of xi if this difference is less than certain threshold, otherwise this. Okay. Whereas if you update it based on this residual, you will be updating it based on yi minus f of xi. So yi minus f of xi, let's say that outlier point 5 is 1 point and let's say prediction is 1.7. It means you're trying to fit a regression model to 5 minus 1.7, 3.3, right? So whereas if you go with the negative gradient, you may be fitting a regression model to much smaller value as compared to this 3.3. It means what? Difference is that negative gradient pays less attention to the outliers, whereas the residual pays more attention to the outliers. So have you got that point? Why is that we have to follow the concept of the gradient than the residual? Because the concept of the gradient pays less attention to the outliers as compared to the residual. Okay, so residual is paying more attention to the outlier points. Got that now? Or shall I repeat it with an example?
Yes.
Repeat.
We have seen now, sir, earlier, just now in example.
Yes, yes. So you got it right. I didn't understand for what you said as for the first question or second question.
No, for the second one, why we should consider the negative gradient rather than the residual? Because
Should
they
I explain one more time?
understood, sir.
Understood. Okay. Okay. Yeah. All right then. So summary of the session is that we are trying to fit an additive model in the forward stage-wise manner. At each stage, we are introducing a new regression model to compensate the shortcomings of the existing model. And the shortcomings are identified by negative gradients. So for any loss function, we can derive the gradient boosting algorithm. So benefit of formulating this algorithm using the concept of gradient rather than the residual is that this concept of the negative gradient is more robust to the outliers than the concept of the residuals. So absolute loss and the Huber loss are more robust to the outliers than the squared loss, right? Because in the squared loss, residual is equivalent to the negative gradient. Okay, but this is not the case for any other loss function. All right, so that's all. Thank you very much and happy learning. If you have any queries, I can take. Otherwise, we can wind up the session because
Session one, sir. It's only much.
Yes. You want me to start another topic? I can start, but that takes
Yes.
1.5.
So this is yesterday's topic, sir.
This is yesterday's topic. Yes, true. But if we start a new topic now, it takes another 1.5 hours. If you are okay with it, we can start. Okay. I don't mind spending time. Whatever is comfortable for you. Okay.
We are in a mode to listen, sir.
Listen. Okay. We'll start. But any queries from here? Okay. Clear? Concept of the gradient boosting is clear?
Yes, sir.
Yes, sir. Yes, sir.
Fine. Fine. Yeah. All right. So the next topic is artificial neural network, ANN. Okay. So in this session, we're going to cover the introduction to the neural network and why do we need the artificial neural network and some motivating examples. And then we will see forward propagation, backward propagation, and the applications of it. All right. So before we try to understand this artificial neural network, let us know a bit about the biological neural network. It means our human brain. So basically, this artificial neural network is designed to mimic the human brain, right? So to do tasks, to perform functions that typically require the human mind, right? So this is mimicking a human brain. It means it is just trying to replicate the human brain. All right. So the artificial neural network is an interconnected group of nodes inspired by the simplification of the brain. So if you look at this example, if you look at this right side figure, what our brain is doing, our brain is taking some inputs and giving some outputs at the higher level, right? So here also, artificial neural network also taking some inputs and giving some outputs to us, right? So similarly, if you look at this, what do you say, the human brain is having around 80 billion to 100 billions of neurons, okay, connected together, right? So you look at this, if you zoom this brain, so you see that it is the interconnection of the various neurons connected together. So similarly, artificial neural network also, we are connecting the artificial neurons. Okay. So the mind can be seen as a biological neural network where it is an interconnected network of various biological neurons connected together. Whereas the artificial neural network is the interconnected network of the artificial neurons connected together, right? So the original goal of this artificial neural network is to mimic the human brain, whereas the current attention is limited to performing specific tasks like object recognition, speech recognition, or mission translation, or gaming, or medical diagnosis, or image captioning, or converting a black and white image to a color image, like that, some specific task, right? So let us try to understand and analyze the artificial neural network. Okay, so as I said, the human brain has around 80 billion to 100 billions of neurons, and depending on where these neurons are located in the brain, they perform certain functionality. Like for example, some part of our brain is responsible for our vision. Some part of our brain is responsible for the audio. Some part of our brain is responsible for interpreting pain and touch. So some part is responsible for some other function, right? So depending on where these neurons are located in the brain, they perform certain functionality. So like for example, if I am talking to you right now, it means some part of my brain is working. If you are listening to me right now, it means some part of your brain is working. So if you could react to the things, it means some part of your brain is working. So if you can interpret the pain and touch, it means some part of your brain is working, right? So this functionality of the neuron depends on where that neuron is located in the brain, where the part where it is located in the brain. But irrespective of wherever it is located in the brain, all these neurons have got some common structure. This common structure has got four important elements, right? So the four important or the main elements of this biological neuron is dendroid, cell body or soma, axon and synapses. Dendroid, cell body or soma, axon and this synapses, right? So these dendroids are like the inputs. They receive the spiking signals from the other neurons. Okay, and width of this dendroid determines the weight associated with that input. Right. So the dendroids are like the inputs that they are receiving the signals from the other neurons. And width of the dendroid determines the weight associated with that input. Now, after the dendroid receives the input, it sends that signal to this soma or the cell body. Cell body integrate all the signals that it is receiving from various dendroids. This cell body integrates all the signals that it is receiving from all the dendroids. If the resulting signal voltage is greater than certain threshold, it passes that signal to this axon, right? It passes that signal to the axon. So axon is like this long tail like structure that you see here that forwards the signal to the other neurons through the synapses, right? So it sends the signal through to the axon. Axon passes the signal to the other neurons through the synapses. So the synapses is like a memory organ in the brain. It connects the axon of the previous neuron with the dendroid of the next neuron. It connects the axon of the previous neuron with the dendroid of the next neuron. So the synapses is acting like a memory organ in the brain. So have you understood these four main important parts of the biological neuron?
Yes, sir. Yes, sir.
Yeah, thank you. So to mimic the biological neuron, we have an artificial neuron. Here also, here the feature vectors are the inputs, feature values are the inputs, x1, x2, x1, xn. And the weight associated with each edge, these are like the dendroid kind of structures in the artificial neuron. And there is a weight associated with each and every edge, similar to the weight associated with the dendroid in the biological neuron. And here we have a function that integrates all these inputs, takes the weighted sum over all these inputs, and it gives it to some activation function. So if the activation function resultant is, if this weighted sum is greater than certain threshold, then the activation function gives the 1 as the output, otherwise 0 as the output. It means that decide whether to pass the signals to the other neurons or the not, right? So similar to that. So here also we are having the interconnected network of the artificial neuron connected together layer by layer, as you see here. So the input is passed to the level 1 neurons, and output of the level 1 neurons is given as the input for the level 2 neurons, and the output of them is given as the input for the next level neurons, and so forth, right? So it means the input is passing through a series of layers and giving you the output in case of the artificial neuron. So we'll try to understand this ANN with a single neuron cell, because this ANN with a single neuron cell is equivalent to the logistic regression model. I hope all of you remember the logistic regression model. Do you remember what is the hypothesis representation in the case of logistic regression model?
1
by 1 plus e to the power minus theta transpose x,
Yes.
isn't it? Right. So that is the representation of the hypothesis. So single neuron cell is performing the same functionality as the logistic regression model. So first we will try to understand the logistic regression model with a neural network mindset. Then we would explore ANN with multiple layers and the neurons. Then we would explore ANN with the multiple layers and the neurons. You can see this. These are the inputs. X0 is equivalent to 1, similar to the one that we have seen in linear regression and logistic regression. And these are all the feature values x1 to xn. And these are the corresponding weights. So the inputs are multiplied with the corresponding weights and taken sum over that. It means W0 x0, W1 x1 plus W2 x2 plus so on, Wn xn. So once you get this net sum, give it to the sigmoid function. So sigmoid function is 1 by 1 plus e to the power minus of this net sum. So this is basically doing 1 by 1 plus e to the power minus theta transpose x. That's all. That's what it is doing, right? So, but this we understood with the mindset of this neural network, right? So the neural network is group of all these neuron units together forms a neural network. So below is the representation of the neural network. So the layer 1, we call it as the input layer. The last layer, we call it as the output layer. In between layers, we call them as the hidden layers. The first layer is the input layer, last layer is the output layer, in between layers are the hidden layers. So here, X0 or A02, we call them as the bias terms, right? So it means the weight associated with that link is acting like a bias unit, okay? So here is the representation of the neuron. It takes the inputs.
So 1 second, sir. 1 second. I think so one layer will have only one bias, sir.
Yes, I mean bias, your node is one, but with this there are multiple weights, right? This weight, right? So for each output node, there is a one associated bias weight. Got it, madam?
Yes.
What I'm trying, yes. Clear? Shall we move on? Madam, who has asked? Geeta, madam.
Yes, yes, sir.
Clear? Shall we move on? Any query you can ask. No problem.
Yes, sir.
Yes, yes.
So for each input, we are along with that input, we are giving weights, no, sir?
Yes. We are not, yeah, we have to learn those weights. That part we will see later. But yeah, weight associated with each and every input. Input between one input node and the output node, there is one weight.
Yes.
Right. You see that this is one weight. This is another weight. This is another weight.
Sir, to give that one.
Sir.
Sir, along with that input, we'll give that weight, no, sir? Is it necessary, sir, to give that
We will
weight?
not give weight. We'll learn the weights. How to learn the weights, we'll see later.
Okay.
Okay. We'll give only input, sir. We'll not give any weights. We initialize the weights, but we'll not give any explicitly. We don't pass any weights. Okay. Fine. So x1 to xk. Geeta madam, your doubts are clear?
Yes, sir. Yes, sir.
Yeah.
Sir, what is perceptron means, sir?
Perceptron, that simple net sum, people call it as a perceptron, sir.
Okay. Fine. Thank you.
That linear regression function is there, no, sir? Theta naught, theta 1, x1, theta 2, x2, so on. That they call it as a perceptron.
Okay, sir. Thank you.
So these inputs are multiplied with the corresponding weights and taken the net sum over that, add the bias term, right? Or you can simply say x naught equal to 1 and the corresponding entry w naught can also act like a bias term, right? Both the things are same. Add a bias term, give it to the sigmoid function, then you get the activation unit. Okay, so this is what a single neuron is doing. So the sigmoid is the activation function. There are other alternative options instead of sigmoid also, right? Like ReLU, leaky ReLU, tan H, like that. Various other alternative activation functions are also there. Okay. So here,
Will we be discussing them also in future or activation?
no. We'll not be discussing that.
In short,
We're discussing the basic introduction to the artificial neural network.
Okay.
So yeah, W1 to WK are the weights. Okay, here B is the bias term. Sigmoid is the activation function. If you see the neural network is passing this input through a series of layers, layer by layer. So this is a neuron in the layer, some layer, right? And these layers are interconnected together layer by layer. This we call it as a fully connected neural network because every neuron in the layer L is connected to every neuron in layer L plus 1. That is why it is called fully connected neural network or multi-layer perceptron. So the input is given to layer 1 and then it is passed through a series of layers and finally you get the outputs. Okay, so the first one you call it as the input layer, the last one we call it as the output layer, in between them we call them as the hidden layers. So if there are number of hidden layers are 1 or 2, we call that as a shallow neural network. If there are more hidden layers, we call that as a deep neural network. There are other architectures in the deep neural network, but discussing all of them is outside the scope of this course. Okay. So here deep means many hidden layers. Deep means many hidden layers. We'll see an example. So here we are passing the input and then multiplying the inputs with the corresponding weights, add the bias term, take the net sum, give the net sum to the sigmoid function. Then you will get the resultant. Similarly, repeat the process for the other neurons also. You will get the output here after giving it to the sigmoid. Give this output as an input for the next layer. Multiply them with the corresponding weights and then add the bias term. Then give it to the sigmoid function. You will get the output. Multiply them with the corresponding weights. Add the bias term. Give it to the sigmoid. You will get the outputs at the next layer and so forth. So if you look at the procedure, what are we doing? We are multiplying W1 with the corresponding inputs. So W1 are the weights at the W1 are the, so you see this. So when you give 1 and -1 as the input, this is what you get as the output. When you give 0, 0 as the input, this is what you get as the output, 0.51, 0.8 with these weights. Okay. So if you see this, different parameters defines the different functions. Okay. So now if you look at this, what are we doing? This is the weight vector, which we got it from here. 1, -2, -1 and 1, right? So to multiply this with the corresponding input, multiply this with the corresponding input, then add the bias term, right? Add the bias term. Then you will get the net sum. Give this to the sigmoid function. So this is the net sum that you're getting, 4, -2, 4 and -2, net sum at this node, net sum at this node. Now give this to the sigmoid function. Give this to the sigmoid function, you will get 0.98, 0.12. Again, repeat the process. Give this as an input for the next layer. It means
Excuse me,
multiply.
sir.
Yes, ma'am.
One small doubt, sir. Initially, do we know how many layers we must use, sir?
While
achieve the
defining the
target?
architecture itself, we define, madam, but how many layers should we consider? Number of layers or number of neurons for each layer, all these are the hyperparameters of the network, madam, that one has to try. Intuitively, you can take the number of layers like this, but that exactly, if you want, you have to tune it to the hyperparameters. Number of layers, number of units in each layer, all these are the hyperparameters to tune. There are some guidelines that people say that based on few inputs you can, I mean, it shouldn't be greater than that, it should be less than this. There are some guidelines for that, but still this is a hyperparameter to tune, madam.
One more doubt, sir. Suppose if any error occurred in between any neuron, so how to detect that, sir? So where is
Error means what, madam? Error means what?
Suppose if we didn't achieve any target value, so there must
That you
be.
will know only at the output layer, right?
Yes, sir. Yes, sir.
In between, you can't know that
Yes,
because
sir.
you're just passing through a series of layers and then finally getting the output. At the output layer only, you know what is the error. So when you know the error at the output layer, you have to back propagate error back to the previous layers. That's how you are adjusting the parameters of the network. It means you have to adjust the parameters of the whole network in such a way that you minimizes the loss at the output layer. That we'll see as we proceed.
Okay, sir. Okay, sir.
Yeah.
Thank you.
Okay, but yeah, is it going okay? I mean, are you understanding that what am I
Yeah.
doing here?
Yes, sir. Yes.
Yes. Yeah. So now you see that if you look at this, we are multiplying these inputs with the corresponding weights W1, add the bias term, then give it to the sigmoid. So that's what, and then you get the activation units, multiply them with the W2, add V2, give it to the sigmoid, and so forth, right? So this is what we're doing. Multiplying input X with W1, add the bias term, give it to the sigmoid. You will get the activation units, A1. Multiply them with W2, add the bias term, and then give it to the sigmoid. You will get A2. And repeat the process till the last layer. It means you multiply WL with AL minus 1, give the add bias BL, give it to the sigmoid, you will get the output units at the last layer. Why? Right. So this is what is the procedure. We call it as a forward propagation. Clear? Is this process clear?
Yes, sir.
Yes, sir.
Right. So here is a simple example of the neural network in which we are taking an example of the digit classification. The digit classification means how many outputs, how many classes? 10 classes, right? 10 digits total, 0 to 9, isn't it? Right. So here take a 16 by 16 image and each pixel value you are taking as the input for the network, right? So it means if there are if the image size is 16 by 16, total 256 pixels are there. It means the input layer size is 256. You see that x1 to x256. This x1 to x256 are going through a series of layers And finally, at the output layer, you have got 10 units. 10 units because there are 10 classes. 10 classes. So each unit indicating the probability of that particular class. So like for example here, this is the unit corresponding to digit 1. This is the unit corresponding to digit 2 and so on. This is the unit corresponding to digit 0, right? So if the 2 is given as an input, what is the true probability distribution? Right, let us say the digits are like this 1, 2, 3, so on 9 and then 0, right? So what is the true probability distribution for input 2? This is 1 and rest of the digits must be 0, right? This is the true probability distribution. It means probability of this instance belonging to 2 must be 1, rest of them it is 0. Hello, am I right? If the input is 2, what is the true probability distribution?
Yes,
0, 1, all zeros, right? Can you now tell me based on this, if the input is 3, what is the true probability distribution?
0, 0, 1.
0, 0, 1, 0, 0.
All zeros.
0, 0, 1, all zeros, right? Yeah. So this is the true probability distribution. So you have to learn the predicted probability distribution close to the true probability distribution. So it means whenever you pass input as a 2, unit 2 corresponding probability should be maximized. Okay. Similarly, whenever you give 3 as the input here, unit 3 corresponding probability must be maximized and so forth, right? So you have to set the network parameters in such a way that whenever you pass input 1, y1 has to be maximum, y1 has the y1 should get the maximum value. Whenever you pass input as a 2, y2 should get the maximum value and so forth, right? So how to let the neural network achieve this is the question. So we understood the process. We also understood that we have to set the network parameters, this W1, B1, W2, B2, so on, WLBL, such that this is achieved. That's such that the difference between true probability distribution and the actual probability distribution is minimized, right? It means whenever the input 2 is passed, the corresponding output should get the maximum probability. We have to learn the parameters in such a way that it happens. Clear? So far, is it clear?
Yes, sir.
Yeah. So now we understood what is a neuron, what is a neural network. We understood what is a biological neuron, what is a biological neural network, and how this artificial neural network mimics the biological neural network. So in that process, we understood what is a single artificial neuron cell is doing, and what is this artificial neural network is doing, right? But now the question is, why do we need this neural network at all? What is the motivation behind this learning this artificial neural network? Okay, so we have so many other models also, like linear regression, logistic regression, and so many other things also. Why do we need this artificial neural network at all? Okay, so let us have a look at that and let us get some motivation through some example. So let's look at how linear regression and the logistic regression learns the complex nonlinear hypothesis. Okay, so if you fit a linear regression model to the data, what is the representation of the hypothesis? Theta naught plus theta 1x when you have only one input variable, right? And what is the second order polynomial representation? Theta naught plus theta 1 x plus theta 2 x square. Can you tell me how many parameters are you learning here? There is only one feature, and if you're going for the linear regression model. 2. If you're going for the second order polynomial,
3.
if you're going for the third order polynomial,
4.
right? Suppose if there are two features, then if there are two features, if you go for the linear regression model, how many parameters you will have to learn? 3.
3.
Right? If you go for the second order polynomial, 6, right?
6.
x1 square, x2 square, x1, x2, total 6. If you go for the third order polynomial, then 10, right? So with 2 features, if you're going for the third order polynomial, you'll be learning 10 parameters. What if you have 100 features? 100 features. Then how many parameters are you supposed to learn at the second order polynomial? How many parameters you're supposed to learn at the third order polynomial? With 100 features, if you go for the second order polynomial, you will have to learn around 5,000 parameters. If you go for the third order polynomial, you will have to learn around 17,000 features, right? It means huge number of parameters you'll have to learn to represent, to learn the nonlinear hypothesis, right? For a simple problem also, right? It means the number of parameters that you're supposed to learn is increasing very high as the number of features are increasing, right? So this is what is the problem with this existing models, right? So how to handle this, right? So the artificial neural network provides a solution for this. So to understand this, let us take a simple example, how to model this kind of data we will see. Before that, let me know whether you know the gates or not. Concept of gates: AND gate, OR gate, XOR gate, NOT gate.
We know, sir.
We know it, sir.
No, right? Yeah.
We know it.
In the DLD or CO course you get, right? Yes.
Yes, sir.
So what is the AND gate? What will you get if you give both the zeros as input?
0, sir.
0.
0, 1,
0,
0, sir.
1, 0,
0.
1,
0,
0, 0.
1.
Right. XOR?
1.
XOR gives 1 as the output if inputs are different. If it is 0, 1 or 1, 0, then it gives 1 as the output. If the inputs are same, then it gives 0 as the output.
0.
XNOR is the opposite of this. Okay. So take you take XOR. So, and let us say the 0 is class 0, class 1 or class 0. See, 1 is the another class 1. Okay. So it means this is y equivalent to 1, this is y equivalent to 0. Okay. So if you take this as a points in the 2-dimensional space, 0, 0, this is the point, 0, 0, right? XNOR it is taking here, sorry, XNOR, right? XNOR, 0, 0 is the input, the corresponding output is 1, which is indicated with the cross mark. 1, 1 is the input, that is also class 1, this is indicated with the cross mark. Zeros, class zeros are indicated with circles, 0, 1 or 1, 0, as you see here. Suppose if you generate more points coming from the similar distribution, you will see the data set something like this as you see in this figure, right? What is your opinion? Is this data linearly separable? Can you draw a line that separates this cross marks with the circles?
No, sir.
Not possible, right? Right. And you see that the learning this pattern is little complex, right? Agree? You see that you will have to learn some model, something like this, which is a complex model, isn't it? Learning this kind of model is tricky, right? It's not trivial, right? Let us see how the artificial neural network learns these kind of patterns. But before that, let us see how to learn a simple patterns using this artificial neuron cells. Okay. So for that purpose, let us take a AND gate. What is the functionality of the AND gate? When both the inputs are 1, then only it is 1, otherwise it is 0, right? This is the output. These are the input 1, input 2. Okay. So 0, 0, 0, 0, 1, 0, 1, 0, 0. This is what we expect, right? And this artificial neural network can model the AND gate. How? Let us see that. With these weights, minus 30, 20, 20. Okay. So what is that we expect as the output when I pass 0, 0 as input? What is that? 0, right? So let us see what it is giving. So this is x not equal to 1 always, right? So 1 is multiplied with minus 30. So minus 30. 0 is multiplied with 20, which is 0. 0 is multiplied with 20, that is also 0. So what is the net sum that I am getting here? Net sum is minus 30. After that, what are we doing? We are giving it to the sigmoid function, z of minus 30. It means 1 by 1 plus 2.71 to the power minus of minus 30, which is plus 30. 2.71 to the power 30. Isn't it a very big number? 2.71 to the power 30. Isn't it a very big number? So what happens when you divide a 1 divided by very big number? What happens?
Infinity.
Negative number we get.
Close to 0, right? How will we get negative number? 1 divided by
But-
infinity is
yes.
0. 0, right? So it's close to 0. That's what we expect. Right. Let us see another value. 0, 1 as the input. What do we expect as an output? 0 only, right? So 1 is multiplied with minus 30. This is minus 30. 0 multiplied with 20. This is 0. 1 is multiplied with 20. This is 20. What is the net sum?
Minus 10.
Minus 10. 1 divided by 1 plus 2.71 to the power minus of minus 10, which is plus 10. Plus 10, right? So 2.71 to the power 10 also very big number. So this is also close to 0. Hello, am I right?
Yes, sir.
Yes. Now next one, 1 0 as the input for this. 1 0 as the input for this. So what is the net sum you get if you give 1 0 as the input?
Minus 20.
Minus 10 again, right? But this is 10, this is
20.
20, this is 20 this time, this is 0 this time. Okay, this is 0 this time. So total net sum is minus 10. This is also equivalent to 0. Tell me, when 1 1 is the input, what do we expect? We expect 1 as the output. Okay, so what is the net sum that you are getting here? Minus 30, 20 plus 20.
Plus 10.
This is plus 10. So z of plus 10. Z of plus 10, right? Z of plus 10 is what? 1 by 1 plus 2.71 to the power minus 10. Minus 10. 2.71 to the power minus 10. Isn't it almost close to 0?
Yes.
2.71 to the power minus 10. So 1 by 1 plus 0. What is it?
1.
1. Right. So with these weights, are we modeling AND gate or not?
Yes.
Similarly, can you model the OR gate? Can you suggest some weights so that you get the OR gate output? What is the OR gate output? When both the inputs are 0, then only it is 0. Otherwise, it is 1. Am I right? Okay. Think of some weights that you get 0 for only 0, 0, but otherwise 1. Think of some inputs, some weights. Some weights. What if I give minus 10 instead of minus 30? Rest of the weights are same. Minus 10. What is the net sum you get when you give 0, 0 as input? If it is minus 10?
Minus 10 only.
Minus 10 will get, right? What is z of minus 10? Z of minus 10 is close to 0. 1 by 1 plus e to the power minus of minus 10. Right? This means 1 by very big number which is close to 0. Right? What is the net sum I get when I give 0, 1 as the input?
Plus 10.
Plus 10. What is z of plus 10? 1? Yeah. What is the value that I get when I give 1, 0 here? 0, 1 here? Or 1, 0? 1, 0 this time.
Plus 10.
0
Plus
over
10 again. Plus 10 again. Z of plus 10 is 1. What is the net sum that I get if I give both ones? 30. What is Z of 30?
+1.
+1. So isn't it OR gate? Right. Like this, some simple gates can be modeled with a single neuron cell itself. Okay. So this is the OR gate, -10, 20, 20. And this is the NOT gate with the weights as 10 and -20. This is not X1 and not X2 gate, right? Which is basically gives 1 as the output when both the inputs are 0. Otherwise, it gives 0, right? This is with the weight of 10, -20, 20, right? So now combine all these neurons together to form a strong nonlinear hypothesis. Okay, so let us see how it does that. So putting all of them together. So this is a neural network which is putting all of them together. You see this, carefully observe. What is this? Isn't it an AND gate? You see observe the weights corresponding to this. -30, another one 20, another one is 20. -30, 20, 20. Isn't this weights? Isn't it an AND gate? Hello?
Yes, sir.
Yeah. So what about this? Not X1 and not X2 gate, 10, -20, 20. You observe the weights corresponding to this one, this blue color one. 10, -20, -20. This is the OR gate. So when you give 0, 0 as the input, what the AND gate gives? 0 as the output. And you give 0, 1 as the input, it gives 0 as the output, and so on. So this is the output of the AND gate, and this is the output of the not X1 and not X2 gate. 1 triple 0, this is 0 triple 0 1. Now you are giving this as the input for the next layer, and that is the OR gate. OR gate, you see that -10, 20, 20. Right, -10, 20, 20. So 0, 1 input, output is 1, 0, 0, 0, 0, this is 0 output, 1, 0, this is also out. Isn't it the functionality that we are expecting, XNOR? Isn't it? One trouble, whenever both the inputs are 0, whenever the inputs are same, then the output is 1. When the inputs are different, the output is 0. Hello? Am I right?
Yes, sir.
Right. It means what? Multiple neuron cells together forming a strong nonlinear hypothesis. And how many parameters are you learning throughout the network? You're supposed to learn how many parameters for this neural network? 3 weights are here, 3 parameters are here. Total 6 are here. 6 plus 3, 9. With just 9 parameters, you are able to learn very complex nonlinear hypothesis, something like this. Right? It means the advantage of the artificial neural network is that it can learn the complex nonlinear hypothesis with a very limited number of parameters also. That is the advantage of the artificial neural network as compared to the other traditional models that we have discussed so far. Clear? The motivation why we need this artificial neural network? Is that point clear?
Yes, sir.
Overloaded? Overloaded?
No, sir.
No. Okay. Fine. So let us go through the algorithm now. Okay. So before that, let us also see some of the notations. So we use a superscript to indicate the layer number. Here superscript 2 means it is a layer number. Subscript is the unit number in that layer, right? So superscript is a layer number, subscript is the unit number in that layer, right? And we use the A for the activation units, Z for the net sum, right? And theta we use for the parameter matrix theta. So theta j is the parameter matrix or the weight matrix between layer j and layer j plus 1. So it means between layer 1 and layer 2 we have theta 1. Between layer 2 and layer 3 we have theta 2. This is a matrix. Okay. And suppose theta j ik is there, right? So this is the weight between layer j and j plus 1, right? And the output unit number is I and the input unit number is k. Okay, reverse. Output unit number is I, input unit number is k. So suppose if this is theta 1, 1, 2, it means this is the output unit number 1. It means this one. And this 2 is the input unit number, which is this. It means theta 1, 1, 2 is a weight between x2 and a12. Right? So is that clear? Notation is clear? Shall we proceed?
Yes, sir.
Yes. So this is a forward propagation. You are taking the inputs, multiplying them with the corresponding weights, and then giving it to the sigmoid function, getting the activation unit A12, which is this. Similarly, taking the inputs, multiplying them with the corresponding weights, giving it to the sigmoid, getting A22. Similarly, you get all the activation units at layer 2, A12, A22, and A32. Now add the bias term. All right, that we'll see anyhow. Now give this to the sigmoid function. Sorry, give this as the input for the next layers, next level layers. Sorry, next layer as input for the next layer. Multiply them with the corresponding weights and then give it to the sigmoid function. Then you will get the activation units at the next layer, right? So here, this is the bias term, theta 101, which is the weight associated with the x0, x0 equal to 1, right? X0 equal to 1, so therefore this will be the bias term. So the bias term will be different for the different activation units. So please make note of that. Okay. Now a question to you. Suppose if there are 3 units at layer 2, 3 units at layer 1, what is the size of the theta 1? What is the size of the theta 1? This is 3 by 4. Okay, 3 by 4, which means this 3 is this, which means number of units at Sj plus 1. It means layer 2. So Sj plus 1 plus times number of units at layer 1 plus 1. Plus 1 because we have a bias term here, right? So this will be of the size 3 by 4. Similarly, if there are 1 unit at layer 3, 3 units at layer 2, what is the size of this theta 2? Size of the theta 2 will be 1 by 4. 1 by 4. This is 3 by 4. This is 1 by 4. Right? So how to handle the multiple classes? That is a single class, only 1 unit. To handle the multiple classes, we take the number of units equivalent to the number of classes. So like for example, there are 4 classes here. Classification of the image as a pedestrian or car or motorcycle or the truck. So we define 1 unit each for each one of these classes. And we want whenever the, please mute yourself because lot of disturbance. Unless you're speaking up something, please mute yourself. So whenever the pedestrian is the input, we want the hypothesis close to 1,000. Whenever car is the input, we want the output distribution, probability distribution close to 0,100. For motorcycle, we want the prediction close to 0,010. And for the truck, we want the prediction close to 0,001. Okay. So it means we want the predicted probability distribution close to the true probability distribution. So if you look at the cost of the logistic regression model, it is taking the cross entropy loss, right? Yi log h theta of xi plus 1 minus yi log 1 minus h theta of xi. Do you remember this? Logistic regression hypothesis, we have derived it through maximum likelihood estimation. Do you remember this? Cost function of the logistic regression model.
Positive and negative.
Yes, sir.
Yeah, and this is the regularization term. So to compute the cost function of the artificial neural network, you just extend this loss function to the multiple outputs. It means compute the loss with respect to each and every output unit, take the sum over that. So here you're taking sum over k equal to 1 to k, additional one more summation over. This is k is the number of classes. So this is just an additional thing, right? And here regularization term is for all the parameters throughout the network, starting from layer 1 to layer L minus 1. So every parameter in the network We use it in the regularization term, except for the bias units, right? Fine. Uh, so that's all very simple. This is the extension of the cost function. So now we have the cost function that we want to optimize. It means we want to adjust the parameters of the network such that this loss is minimized, this cost is minimized. Do you know any algorithm to do this? How do you optimize the parameters of the network such that this loss is minimized?
Gradient descent.
Gradient descent algorithm, right? So it means compute the gradient with respect to each and every parameter in the network and apply the gradient descent algorithm. Theta equivalent to theta minus alpha times the derivative of j with respect to theta. Every theta in the network. I mean every theta ijl in the network, right? So we have to compute the gradient with respect to each and every parameter in the network and then update them using the gradient descent algorithm. That means theta equivalent to theta minus alpha times the derivative of j with respect to theta. Now, what is the problem with this approach? This is a brute force way of learning the parameters. Okay, so if you compute this parameters through this approach, lot of redundant computations you will have to do. So the brute force approach is compute the gradient with respect to each and every weight, apply the gradient descent algorithm to update the weights. So this process is time intensive and lot of redundant computations will have to do. So what is the solution for this? Solution for this is the backpropagation algorithm. So backpropagation algorithm is a kind of dynamic programming. Dynamic programming. You know dynamic programming, right? All of you, I'm assuming that most of you are from computer science. So dynamic programming concept is what? It
Store the
computes
previous solution to the
Yes, sir.
next.
So yes, exactly. It means it computes any quantity that is of interest only once and it stores them. Whenever it has to compute the same quantity again, it will refer to the table and it access that value instead of recomputing it again. Am I right? Right. So it means it is avoiding redundant computations by storing the solutions or storing the quantities that are of interest, right? So through this way, it is avoiding the redundant computations. Similarly, in the backpropagation algorithm also, we does the same thing, right? So it computes any quantity of interest only one time and it reuses this multiple times. Through that way, it avoids lot of redundant calculations. Okay. So we'll see the forward propagation first. We take the activation units at layer 1 as the inputs, multiply them with the corresponding weights, we'll get the net sum. Give this net sum to the, add the bias term and then give it to the sigmoid function. You will get activation unit 2. Multiply them with theta 2, add the bias term, give it to the sigmoid, repeat the process till the last layer. You will get the hypothesis at the layer L. Activation unit L is the layer, is the hypothesis representation. Now this is the forward propagation. Is it clear, the forward propagation? Starting from the input
Yes,
layer,
sir.
going through a series of layers, finally getting the output. Output that you're getting is h theta of x or AL. That is the prediction. Okay. So in order to reduce the error between the prediction and the actual value, we use the backpropagation algorithm. So once you go to the last layer, compute the error. Error is what? The difference between actual and the predicted. Okay. This concept that I'm going to demonstrate now, this is with respect to true with respect to the squared laws, but I mean this delta L concept is true with respect to the squared laws, but not with other loss functions. But that avoiding redundant calculations is true with respect to any loss function also. That also I will demonstrate. I will explain. Okay, I don't have a separate slide, but I will explain. Fine. So once you go to the last layer, compute the error. Error is the difference between prediction and the actual value y, right? So compute the error at the last layer. Now propagate this error back to the previous layers, right? So let's say that I have given some task to Geeta madam and Ravi sir. Okay, so let's say that our Geeta madam and Ravi sir gave some task to some other student. All right. So now let's say that when I give this task, Geeta madam contributed some 45%, Ravi sir contributed 55%. Now something went wrong in that. How much share of the blame should Ravi sir take? How much share should Geeta madam take?
55% for me and 70% for me.
55% Ravi sir should take because he contributed 55%. 45% Geeta madam should take because she contributed 45%. So if some error occurs at the last layer and many nodes at the previous layer contributing for this output with some weights, isn't it? So when you're propagating this error back to the previous layers, you'll be multiplying them with the corresponding weights only to get the error at that node, isn't it? Right. So to propagate the error back to the previous layer, delta L transpose delta L plus 1, right? And this is the derivative of this with respect to ZL, right? So you're computing this, computing the error term at the previous layers. So the process is very simple, don't confuse. Through forward propagation, you compute h theta of x or AL, which is same. So once you get the hypothesis or the prediction or AL, compute the error at the last layer, AL minus 1. Now this is the error at the last layer. Propagate this error back to the previous layer. It means you compute delta L minus 1, delta L minus 2, so on till delta 2. Right? We'll stop at layer 2 because we assume that there is no error associated with the input layer. Right? So compute the error terms back to the previous layers. Once you compute the errors, you can make use of the errors to compute the gradient directly, right? So derivative of j with respect to theta ijl is equivalent to ajl times delta il plus 1. This is how we compute the gradient. I'll show you, don't worry about this, but just think of this like an elegant way of computing the gradient. Okay, see, lot of calculations it avoids. It directly computes by using the activation units. It is computing through forward propagation. Error terms it is computing through backward propagation, right? Just compute them once, stores them, and it uses them whenever it has to compute the gradient. That is why we said it is a kind of dynamic programming. Okay, so we'll see the algorithm, then I will explain through the example why is that both of them are equal. Okay, so don't worry about that part. Just till I demonstrate the example, just follow the procedure. If the procedure is clear to you, that's fine. Is the procedure clear to you so far?
Yes, sir.
Yes. Okay, so let us summarize the algorithm. We are given a training set x1, y1, x2, y2, so on, xm, y1. So we are initializing all the delta values, gradient values to the 0, right? So this is process repeated for all the instances I equivalent to 1 to m. We are setting the activation units at layer 1 to the input, and then we perform the forward propagation, right? It means we are computing activation units at layer 2, layer 3, still layer L. Once we get the prediction AL, we compute the difference between prediction and actual value, which is the error at the last layer, delta L. Then using the backward propagation, we are computing the error at the previous layer, delta L minus 1, delta L minus 2, so on till delta 2, right? And now we are computing the gradients associated with each and every weight using this formula. Then summing, adding them together and finally taking the average value here, 1 by m, delta ij L. So for j equal to 1, there is no regularization term associated with that. That is why there is no additional term here. If j not equal to 0, there is a regularization term also you can consider there. Okay, so finally, this is the final gradient value, right? Which is the average of the all the gradients with respect to each and every example. Okay, now once you get these gradients, you can update them using the gradient descent algorithm. Okay, so we'll see now.
So once again, previous slide, previous. Last.
Previous.
Yeah.
Yes, madam. Corey.
This last one, which is there in the rectangle box, no, sir.
That is the vectorized implementation of the same thing, madam.
Oh.
I mean, instead of updating one by one, that whole thing is shown like a vectorized form. Same thing. Yeah. Clear, ma'am? Shall we move on?
Yes, sir.
So here is an example. So let us solve example. In the example, I've ignored the bias term just for the sake of simplicity. If you want, you can add, no problem at all. Okay. So I've ignored the bias terms. So two inputs, x1 and x2. Multiplying x1 and x2 with the corresponding weights and getting the net sum corresponding to z1, this one. Give it to the sigmoid, you will get a12. All right. Multiply the weights with the corresponding, multiply the inputs with the corresponding weights, and you will get the net sum here. Give it to the sigmoid, you will get the activation unit at this layer. Now take this as an input, multiply them with the corresponding weights, right? Multiply them with the corresponding weights, you will get the net sum. Give it to the sigmoid, you will get a13, which is also the output h theta of x. So this is forward propagation. Forward propagation is clear so far?
Sure.
Yes, sir.
Yeah. So now, suppose I want to compute the gradient with respect to this theta 112. Okay, and this there is only one output unit. So the loss function is this, is similar to the logistic regression cost function, right? So suppose if I want to update with respect to this weight, okay, so using the back propagation algorithm, this was the formula that we have seen in the previous slides. Derivative of j with respect to theta ijl is equivalent to ajl times delta I l plus 1. Okay, so now if I want to compute the gradient with respect to theta 112, okay, so what is I value here? What is j value here? What is l value here in this example? I is 1, j is, tell me, what is j?
1.
1. And what is l value?
2.
L is 2. Okay, substitute in this, j value is what? 2. J value is 1, sorry. J value is 1. So A1, L value is 2. A1, 2. So this is first thing. What is the second one? I value is also 1. And L plus 1 is 3. Delta 1, 3. This is what we get, right? Through the formula. Hello? Am I right?
For
This is what we get through the formula.
is 3 only, no, sir?
Ramya madam, your
Yes,
voice
sir.
is very low. Please speak little bit loud.
Sir, AL is 3 only, no, sir? The last layer is 3 only, no, sir?
Nine. So you are computing with respect to delta 112. 112, what is L? L value corresponding to this is this, right? 2. I didn't get your point. This A13, L is 3. But you are talking about this weight, right? Delta theta 112. So the weight in between layer 2 and layer 1 is theta 2 only. Weight matrix between layer 1 and layer 2 is theta 1.
Okay, sir.
But, yeah. So I'm talking about this weight, madam. So just try to map these notations with these weights. What is I value? 1. J value? 1. And L value? 2. Right? So substitute I, J, L values in this, you will get this. Okay, as simple as that. Clear, madam? It is through formula, direct formula. I'm trying to map this with the general calculation of this computation of the gradient. Till this point, is it clear, madam? Ramya madam, Tipa madam, Ravi sir?
Yes, sir. Yes, sir.
Everybody, yeah. Yash is silent these days. I don't know why.
So it is going very well, sir.
Okay. So now let us compute it through the brute force approach, right? So derivative of j with respect to theta 112. So using the chain rule, I am writing it this way. derivative of j with respect to h theta of x, derivative of h theta of x with respect to z13, and derivative of z13 with respect to theta 112. So I break it using the chain rule. Derivative to simplify the situation only. There is no other reason. Derivative of j with respect to h theta of x, derivative of h theta of x with respect to z13, and derivative of z13 with respect to theta 112. Right. So let us compute the individual terms. Derivative of j with respect to h theta of x, which is this. J is this. Incoming voice. Okay. So what is the derivative of log x with respect to x? 1 by x.
By x.
Right. So what is the derivative of log h theta of x with respect to h theta of x? 1 by h theta of x. Right. Yi 1 by h theta of x. And what is the derivative of log of 1 minus h theta of x with respect to h theta of x? 1 divided by 1 minus h theta of x, and derivative of that is minus 1, which is this. Right. So when you take it with respect to h theta of xi, this will not be there. This will be yi minus h theta of xi divided by h theta of xi times 1 minus h theta of xi. Right. You can solve that. When you take this LCM here, h theta of x times 1 minus h theta of xi, and this is yi minus h theta of xi. Yi minus h theta of xi. Right. So this is what you get. All right. So now, clear? Is this clear? The first term is computed. Clear? And you got this as the output. Y minus h theta of x divided by h theta of x times 1 minus h theta of x. That's what you got. You can expand this and you see you will get that. The first term is computed. So is that clear so far? Everyone?
Sir.
Everyone?
Yes, sir.
Yes, yes. Now let us compute the third term. Derivative of z13 with respect to theta 112. Z13 is this. Take the derivative of this with respect to theta 112. So this part will become 0 because no theta 112 here. So here is a theta 112 here. You will get a12 as the output. A12 as the output. So for the third term, we have got a12 as the output. What we left with? We left with this derivative of h theta of x with respect to z13. Okay. So what is h theta of x? H theta of x is sigmoid of z13. Okay. So when you're taking the derivative of h theta of x with respect to z13, it means you're taking the derivative of sigmoid of z13 with respect to z13. Isn't it like sigmoid of taking the derivative of sigmoid of x with respect to x? Hello? Isn't it like that? Taking the derivative of sigmoid of x with respect to x? Hello? Oh, exhausted. Following or not? Nobody is answering.
Following, sir.
Okay. Fine. So it is equivalent to taking the derivative of sigmoid of x with respect to x. When you take the sigmoid of x with respect to x, we call it as the sigmoid dash of x, and that is equivalent to sigmoid of x times 1 minus sigmoid of x. So using this, can I say can I say sigmoid of h theta of x with respect to z13 is equivalent to h theta of x times 1 minus h theta of x? Or equivalently sigmoid of z13 times 1 minus sigmoid of z13. Can I write this using this sigmoid of x times 1 minus sigmoid of x?
Yes, sir.
Sigmoid of z13 times 1 minus sigmoid of z13. Sigmoid of z13 is h theta of x. H theta of x times 1 minus h theta of x. So this is sigmoid h theta of x times 1 minus h theta of x. Please remember that. So the second term is h theta of x times 1 minus h theta of x. Whereas for the first term, this h theta of x times 1 minus h theta of x is in the denominator. So this and this will get cancelled. And what you will get as a result? yi minus h theta of x, y minus h theta of x times a12. And what is this y minus h theta of x? Isn't it the error at the last layer? Delta L, where L is 3. Hello? Isn't it the error? So y minus h theta of x is delta L, which is delta 3, 1. Right? And this is a12. Right? So what is that we got it through this process? A12 delta 13. And through this process also we got the same. Hello? I'm just trying to prove that. Is that point clear? Even if you don't understand the whole derivations, the point that I would like to stress here is that whatever that you are getting through this redundant computations and whatever you are getting through this back propagation algorithm, both of them are same. I just want to make that point. Is that point clear?
So only that next slide. This omega control also.
Where is omega? Delta.
Delta.
Sorry, sigma, or delta.
Sigma.
This one. Do you want to explain?
Alone. Left side, sir. Derivative alone.
You want me to explain this?
Yes, sir.
Yeah, madam. See here.
Yes, sir.
Sigmoid of x is 1 by 1 plus e to the power minus x. Okay. So we are now taking the derivative of sigmoid of x with respect to x. Okay. These are all computation internally. You can slowly go through it later because there are multiple rules involved here. I'm not going to touch that. Okay. But when you compute the derivative of sigmoid of x with respect to x, what we got here is that sigmoid of x times 1 minus sigmoid of x. It means derivative of sigmoid of x with respect to x is equivalent to sigmoid of x times 1 minus sigmoid of x. So we are making use of this. And now suppose if you want to know derivative of sigmoid of z13 with respect to z13, can I use this formula?
Very well, sir. We can use.
It means sigmoid of z13 times 1 minus sigmoid of z13. Am I right, madam? Ramya, madam?
Yes, sir.
So what is sigmoid of z13? It is the h theta of x. You can see that z of z13 is h theta of x times 1 minus h theta of x. Now you got this. Substitute this in the chain rule. This is h theta of x times 1 minus h theta of x. But for the first term, the same term h theta of x and 1 minus h theta of x is in the denominator. So this denominator and this numerator will get cancelled. So you leave with yi minus h theta of xi here. And from the third term, you have got a12. So yi minus h theta of xi is error at the last layer, right? Delta 31. And delta 31 times a21. This is what you got, which is the same thing that you have got through this backpropagation algorithm formula.
Yes, sir.
Clear, madam? Now?
No,
Yes, sir.
not
Now I
clear,
got
sir.
Yeah. So now let us say you want to one more point. This is one point I want to demonstrate. There is another point also. Please do focus. Unless you focus, it is difficult to follow. So now you compute. Let us say that you want to compute this derivative with respect to theta 112. Sorry, 111. This one, right? 111. So when you took this derivative of 1111 using the chain rule, derivative of j with respect to a13, a13 with respect to z13, z13 with respect to z1, a12, a12 with respect to z12, z12 with respect to theta 111, right? So all these chain rules. So now please see that have we computed derivative of j with respect to z13 already in the previous one? This is already computed, right? Right. So this is already computed. Why to compute it again? So the backpropagation algorithm elegantly making use of already computed one. That's the reason why it is taking the corresponding error terms. right? So it is multiplying with the corresponding previous error terms to get these redundant calculations without having to recompute them again, right? That's the beauty of the backpropagation algorithm, right? Similarly, here everywhere that the A1 like, so this is what you get when you compute, but you observe that all these terms are already computed. A12 is already computed, A11 is already computed, y minus A13, that is the error term, is already computed. So it means it is just making use of whatever that is already computed in the backpropagation algorithm. Therefore, it is avoiding the redundant computations, hence it is saving a lot of time, right? That's the advantage of the backpropagation algorithm instead of going for the brute force approach, right? I just want to make that point. I hope that point came out clear. Is that clear?
Yes, sir. Yes, sir.
Fine. So even if you are a faculty, if you are trying to tell to the students, I see that more, I mean, I'm not talking about you. In general, I'm talking. I saw that many people say that this is the forward propagation algorithm, this is the backward propagation algorithm, but never I saw that people explaining what is the intuition behind the back propagation algorithm. Why is that we are doing this way? So if you are a faculty, I request you to explain that whenever you are explaining to your students. Okay.
Sir, just go back to the diagram, sir. Just one doubt, last doubt. Yeah, previous one, sir. Sir, here after computing theta 1, we are actually propagating error over the backward. So updated value should be multiplied with the error, and you will get error at A12 subscript superscript 2, isn't it? Is it right?
No. The error term still here only you will get. There is, we will not compute error associated with the layer 1. Okay. So there is, because we assume that there is no error associated with the input. So we'll stop that error computation.
No. Sir, back layer H0, actually error at A13, the output is back propagated to A12.
Yes, delta
So
2.
theta 11 is updated at that time, isn't it?
Yeah, when you are computing with respect to delta 2, you are saying, right? Yes,
Yeah.
yes, you're right.
And we use that theta for backward propagation. Theta 11.
Nee, theta 11, see, theta 11 is that in between layer 2 and layer 1, right? So you will not propagate the error back to the layer 1. You will stop here. That's what I'm saying. Okay, because this is a small layer, small network, you are confusing. But see that, so you're starting at here and you will propagate till here only. Okay, so you will not, it means delta 3 you compute, delta 2 also you compute. Okay, and make use of them. Delta 1 you will not compute.
Sir, just one last one. I see that pattern that if you want to compute update theta 11, so error term at the downstream
Theta
node.
1, right, sir? So you see that what is I value? I value is 1, J value is 1, L value is 1. Okay. So you see that you will be doing A11 delta 1 2. This is what you need A11 and delta 1 2. Got it, sir?
Sir, actually, we actually first we thought when we are performing back propagation, we are giving this error right from the first layer, and we are trying to correct it right from the first layer, then second layer, then third layer.
No. Error is propagated backward, madam, not forward. You will first compute delta 3, then delta 2. Making use of delta 3, you will be computing delta 2, and so forth. So that is what is mentioned in the algorithm also. You see that. Compute delta L minus 1, delta L minus 2, so on delta 2 using back propagation. So how is that computing also mentioned here? The delta L is theta L transpose times delta L plus 1 times Z dash of ZL. This is what in fact you are doing now here. This one. The whole thing is what? Delta 2 only times A11. That's what you're doing, right? That's why I'm saying that you compute this, you will avoid all the redundant calculations. That's why it said. You see that? You just make a connection between everything. See that you're performing forward propagation A1, A2, so on till AL. After once you go to the last layer, compute the error, which means the difference between AL minus Y. This is the delta L. Now propagate the error backward. It means compute delta L minus 1, delta L minus 2, so on delta 2. Now make use of this back propagation terms and the forward propagation terms to compute this gradient. That's all. Simple.
Thank you, sir. It was a very big misconception now. Now it got cleared.
Sir, I forgot. Ravi, who has asked the question? Ravi?
Sir, Parmesh, sir.
Paramesha, sir. Yeah.
Sir, you will just go back, sir. Previous one. Forward, sir. Diagram. Sir. Sir, here delta 2, you are computing by multiplying with weight, updated weight, theta 11, isn't it? When you back propagate, you are computing weight at the output layer. That is again
Multiplying with
transmitted.
this.
That will become delta 2 at A or 1, isn't it?
No, here delta 2 at this layer.
That is obtained by multiplying with theta 11, isn't it?
Yes, sir. This is the delta, this one. You're multiplying with theta 112 and sigmoid dash of A12, you will get this delta 2. I mean, this whole thing is delta 2. This is the delta 3, sir. Delta 3, this one. Multiplying it with the weight and then this sigmoid dash of A12 that you can see here, that formula. Delta L transpose delta. This is the for whole thing you're computing, delta L plus 1 times Z dash of ZL, which is the same thing there. Got it, right?
Okay.
Got it, sir? Parmesha, sir. Is it?
Got it, sir.
Don't confuse, yes. So, yeah, basically you are using that. Okay. So, application of ANN, many. It's difficult to find a domain that doesn't have this ANN application. Character recognition, signature verification, face recognition, machine translation, speech recognition, captioning an image, optimizing the color curves, predicting the next word. That's not a direct application of this fully connected neural network, but there are other architectures of the neural network, that sequence modeling and recurrent neural networks. There are many applications. Here is one example, character recognition. So this is the ODI character recognition. Features are extracted explicitly. There are 4 important regions identified by the domain expert, highlighted with the boxes as you see there. And these boxes are projected in 4 different directions: horizontal, vertical, left, right. So 5 boxes, 4 directions, 5 times 4, 20 features. 133 classes are there, around 10,000 instances. And about this data, I think it was taken from that IIIT Hyderabad. This was my guide's work. Okay, Professor Arun K. Pujari's work. He is from Odisha. So even I was doing some work on this. I mean, that's why I kept it here. So about 95% accuracy we've got. Okay. So that's all. Thank you very much and happy learning. Demonstration, shall we see it tomorrow?
Okay.
Sure, sir.
Yeah.
Okay.
That's all. Thank you. Happy learning.
It was superb, sir. Thank you, sir.
Yeah.
Thank you so much,
Thank
sir.
you.